Yeah, okay.
Yeah,
So
but
I'm here presenting on behalf of the anonymous team called Cartesi Nakamoto. Um, and it's about a team that was completely crazy because they want to put Cartesi on Bitcoin. And actually, I'm just hosting a copy of the repository, right? So this will have a lot of turtles in it. And because we are starting out with something with a very, very small amount of computation and bigger and bigger and bigger. I'm kind of like seeing how we can get to it. So moving on a little bit, if we can get this to go forward. So a lot of you probably have complained a lot about difficulties of developing with EVM and Solidity, and I can tell you that Bitcoin script is so much worse. And it's basically, it's not really expressive enough to kind of like do most computation. Like, for example, it's completely impossible to combine two 32-byte values into a 64-byte value and hash it. Basically, they have taken away the kind of like the instruction that combines two byte strings together. So you can't do a Merkle proof verification. And the way that kind of like Bitcoin works, just a little bit of highlights here, is you can kind of submit along with a transaction some data to a Bitcoin address and spend the value in that address if that script that hashes to that script address allows you to, and you kind of have to send along the script when you spend it. One of the new things in Bitcoin network is something called Taproot, which is basically you can have a Merkle tree of scripts, and kind of like you can pick a particular script when you are submitting a transaction to kind of like pick which script is supposed to work. And basically the reason why these opcodes are not there is because Satoshi Nakamoto himself during Bitcoin crash basically panicked and disabled everything that could potentially cause any trouble. And they were just never re-enabled because, well, change is a very hard thing in Bitcoin. So one thing that got introduced, and just to show how bleeding edge this is, people have introduced something called BitVM here in the beginning of October by Rob and Linus from ZeroSync. They have also previously made a ZK proof of synchronizing to the Bitcoin blockchain. And what they kind of introduced here is a new trick, where you can basically have a bit commitment, which is basically a way to keep a particular value exactly the same across multiple Bitcoin transactions, and kind of like making what they have what's called logic gate commitments. And this new approach of doing things is basically attracted quite a lot of attention. There's almost 900 people in the BitVM Telegram group, and I thought this is interesting. And basically what they allow is between two parties, approve or verify, you can kind of like take a Boolean circuit, it's a little bit explained up in the corner, and compute this and kind of like dispute if the proof of computed the circuit correctly. And the verifier is also able to kind of control some parts of the inputs of the circuit. And back when we started with this hackathon, like it was 1% success chance for having anything working. Like basically people were handcrafting circuits. And there's still this restriction of having two parties. And one of the kind of the early things we started doing before kind of like getting a little better idea how to do things was basically making programmable lookup gates by using this type of Merkle tree, a little bit like a ROM, taking 8 bits of lookup and getting a constant answer back and doing some computation. But this is kind of like the boring part. So why Cartesi and VM? Because like the typical reaction of most communities is to implement custom virtual machines, tooling, compilers, and well, Cartesi is nice because we already have VM, which we can execute without executing a circuit. We already have microarchitecture code, which is kind of like implementing a very small basic instruction set. And we can use existing compilers. We don't need to make a new compiler. We can reuse the existing test cases. So it means that basically we can be much more confident that whatever we're building is actually functioning correctly, and we can have much less time to production. And also that all Cartesi state is memory, making kind of like ideal for finding kind of like the point of disagreement. There's a small explain about terminology here, but you can kind of like read the slides afterwards if you want to hear about that. So writing circuits by hand is hard. So we basically had two choices for the team, which I might or might not be part of, which is that we can either handwrite a RISC-V circuit, which is excellent thing to do, but if you have better things to do in life, then you're probably better off finding a completely undocumented 3 to 5 years old academic software that's described mostly in an academic paper that turns C code into a Boolean circuit. And that's basically what we found, which is called HiCC. And it's basically using bounded model checking to turn into Boolean circuits. And we can spend some time getting it to build on modern platforms, which is impressive considering that things are breaking after they haven't been built for 3 to 5 years. And got a Docker image for it. You can find at this repository address. And also kind of like one of the benefits we got for this was that there's also a circuit simulator, so we can quite easily kind of like test the circuit. And a lot of lessons were learned, like for example, that we need to basically make all loops that we're dealing with be unrollable, as in they have to be written out in particularly, how to make optimal Boolean circuits, deal with bugs, how to make separate Boolean circuits that can't get merged together, because basically we ran out of memory and one compile builds took 9 hours at some point, and that we basically had enough. We tried a lot of other circuit compilers, and there was one that was a very nicely academic paper, and it couldn't handle a single freaking if instruction. And then we also began some work to kind of like start building a little bit of Rust-based tooling for the PIC-VM, because the current one is in JavaScript and doesn't scale big circuits. And what we then did was the kind of the obvious thing was basically taking the excellent work done on the Cartesi machine, the microarchitecture from C++, converted into C, which is thankfully easy because it's C++, and we built it, and then kind of like made memory reads and writes through access logs, as in when CPU is kind of like accessing particular registers and writing out to memory and writing out cycles, and we managed to kind of cook it down to a quite nice little circuit of 33,000 circuits with a depth, as in how long is the potential longest evaluation of it. And at that point, okay, does this thing actually work, right? And that's where the tests that we already are using in the Cartesi project came in handy, and we kind of made a script that converted from the test JSON to the circuit simulator, and well, basically, pretty much in the first try, all the tests passed. Now, this is also a C implementation of Cartesi microarchitecture. It's kind of used for elsewhere, like, for example, in secure multi-party computation, embedded boards such as Arduino. For example, if you want to outsource computation to untrusted clouds, we just need a few and they can kind of like dispute back. If you want to compile it to BPF like Solana, or for example, lost outputs out of this as well. Right? So what we very quickly find out is that when you want to kind of prove that a particular piece of memory is in a Merkle tree, you basically need to do a lot of Merkle tree verification, like the way that we kind of like hashing a state in Cartesi machine environment. And we're using Ketchak 256, right? It took us quite a while to kind of find a tree implementation that matched, and we found a way to kind of make it a Ketchak algorithm. Well, basically 64 bytes of hashing took 166 K gates, and 60 million for hashing 8192 bytes, and basically it got a little fat when we had to do 16 possible memory accesses times 61 Merkle proof verification hashes together with this amount of gates. So basically, we didn't want to kind of build an extremely high circuit that basically it would take too long to basically to compile. So instead, since we have microarchitecture, then we decided that we are going to introduce the nano architecture, which are here smaller than a microarchitecture. And basically what we did then was to use the fact that we don't feel limited by the input size. Of course, the RAM size in this particular case affects the circuit size, but we wouldn't want to have kind of like a 64-bit byte address space. So kind of like we made it tiny. So we used the same circuit as we had before, but we just basically stuffed in 8 kilobytes of RAM, which includes the code and CPU states and so on, and then making that virtual machine bisectable. So we can do kind of like 30 bisection steps, which gives us about 2 to the 30th of RV64 cycles. How this works exactly is that we can have the verifier pick 30 bits of input, where it kind of gives agree, disagree, as the Google reveals the bits of machine state at particular points. And then the circuit itself does the bisection and concludes kind of like machine states where the prover and the verifier agrees, and the state right after where they no longer agree, and then runs the step from that and kind of claims if it is. We ended up with a circuit about 28.3 million gates and a depth of 392, right? And basically, we ran out of time at that point because we had spent 2 days compiling circuits. That took a little too long time, but basically we ended up at the point where we are free of kind of like circuit size constraints, and now instead we're limited by the amount of cycles we run on top of it and kind of fitting our code in state and RAM. So what we now can do, instead of using a circuit compiler, is we can use existing RISC-V backends to compile to this tiny little machine, compile our circuit again, but with hashing, and have it run a step and Merkle-proof verify all the memory accesses and kind of gain the whole 64-bit memory that we kind of like use based on a Merkle root. And also we can kind of like have a shared kind of like ROM area, which is the input to this, that we can have access to all nano-arc cycles in order for us to actually implement, let's say, a micro-architecture bisection. And as some of you might know, if you have a micro-architecture bisection, we can basically go out and run a full step of RV64-bit computation, and that would mean essentially that we can run Linux-based computation of Bitcoin throughput between 2 parties, currently approved by verifier. So maybe in a couple of weeks we are able to actually do this. Some problems is that kind of like the BitVM tooling is not exactly there yet, as in it will definitely blow up if we put 28 million gates in there, but turtles upon turtles upon turtles, and this would actually work. Oh yeah, that's it.
I'm speechless. I don't know what to what to say. I guess the chat said it all.